All right, so I just wanted to run over these last two problems at the end of chapter 6. I know I already went over the first one yesterday in class, but I was rushing a little bit. Plus, I had another website I wanted to show you that you could use to plot the distributions if you want. So anyway, just looking at this problem number 1 first. So we're sampling air. Each sample has a 10% probability of containing this rare molecule, and we're going to take a total of 15 samples. So the success, what we're looking for is, does it contain the rare molecule? Okay, that's what the whole topic is. The sample size is 15 because we're going to take 15 samples. The probability that any one sample will contain the rare molecule is given at 0.10. All right, and then I had told you guys kind of right off the bat, hey, why not just look the probabilities up in the table? All right, so here is just an excerpt from the table for the sample size of 15, and then we want to be in the right column. The probability of success is 0.10. So problem A, the probability that none of the samples contain the rare molecule. So that is just asking you to find P of 0. All right. So again, and we already went over this, just go to the table and look. Right here is the probability of X equals to 0. So it's 0.2059. Part B, find the probability that at least one. Okay, so at least one out of the 15. And again, keep in mind that X could be 0, or it could be 1, or it could be 2, or it could be all the way up to 15. Okay, those are the possible values of the random variable. Those are the possible number of, out of the 15 samples, how many could possibly contain this rare molecule. At least one would be 1 or 2 or 3 or all the way up to 15. So in other words, all of these, 1 through 15. So what you could do is you could come to the table and you could add up all of these probabilities. So probability of 1 plus 2 plus 3 all the way on up. That's one way to do it. Or the only one you don't want to include is 0. So it's easier to just do 1 minus P of 0, especially since you already found that in part A. So if you do 1 minus that, then you get 0.7941. All right, part C, the probability that at most 1. Okay, and again, so much of this is just interpreting the words correctly. So in this case, at most 1 would mean it could be 1, but it also could be 0. Either one of those falls under the category of at most 1. Okay, so you have to add those two probabilities, P of 0 plus P of 1. Right, and if you add those, you get 0.5491. Part D, find the mean and the standard deviation of the number of air samples that will contain the rare molecule. All right, so we went over the formulas already. The mean is equal to N times P. So N is 15 and P is 0.1. All right, so you find that the mean is 1.5. So on average, if you did this many times, took 15 samples of air at a time, on average you would expect about 1.5 of them to contain this rare molecule. All right, and then sigma equal to the square root of n times p times 1 minus p. N is 15, the sample size. P is 0.1, and therefore 1 minus 0.1 is 0.9. So if you take the square root of all of that, you should get 1.1619. Or you could round that off to about 1.2. What will the shape of the probability distribution look like? And how do you know? All right, so at this case, at this point, I'm gonna erase everything that I've written and go back a couple pages in the handouts. All right, so what we're referring to when we're talking about the shape is if you come back up to this page, the shape of the distribution. So there's two different things that can affect the shape: the probability of success and the sample size. In this case, our probability of success is 0.1. It's much less than 0.5. So it's more like this because RP is 0.1. So that will tend to make the distribution lean to the left and be right skewed, but it also depends on the sample size. And in this case, our sample size is 15, which is not huge. So again, we would think that we're probably going to be here with a very right skewed distribution. But we can test it, and I had given you this rule of thumb right here yesterday. If n times p times 1 minus p, if it is large, in other words, if this is greater than or equal to 10, so that implies that the trial size is large enough, then it will be bell-shaped. But for the problem that we're looking at, if we do that, so our trial size is 10, our probability of success is 0.1. Sorry, our trial size is 15. I'm not sure if that's what I just said. Probability of success is 0.1, and then 1 minus that is 0.9. And if you calculate that, it is equal to 1.35, which is clearly much less than 10. So that is how we can conclude that the shape of the distribution will be right skewed. All right. All right, I'm going to erase again. And then I'm also going to show you on a different website how you can actually just plot these distributions. All right, so I'll post this link, but if you just go on Google and Google plot binomial distribution, this should come up first. It's at University of Iowa. All right, so if I just go ahead and put in my trial size, 15, my probability of success, 0.1, and then I hit enter, all right, it will make a very nice plot of the binomial distribution for us. And as we already knew, you can see it is very right skewed. Also, this is nice because it will calculate the mean for you down here. It will calculate the standard deviation for you right here. And you can also, it doesn't print out the whole probability distribution the way StatDisk does, but we can calculate for particular values. So for example, in part B of the problem, we had calculated the probability of at least 1. So for example, I can put in x equals 1, and then I can calculate the probability of it being greater than or equal to 1, 0.794. That's exactly what we had just calculated. Or part C, we had calculated the probability of at most 1. So in other words, that would be less than or equal to 1, 0.549, exactly what we had just found. All right. All right, and then let me go back down to the last part of the problem. Would it be unusual for 4 of the air samples to contain the rare molecule? Now, we just saw that it was right skewed. So when you're checking for unusual results, you can only use the empirical rule if it is approximately bell-shaped. This distribution clearly not bell-shaped, so we cannot use the empirical rule. In other words, we have to use probabilities. So we are looking for 4 of the air samples. Now, if I come back to the plot, notice that we know that our mean is about 1.5. It is exactly 1.5 right here. So the value we're interested in is 4 unusual. It is clearly to the right of the mean, which means that I'm looking at this side of the curve. So remember, I can't just look at P of 4. I have to look at P of 4 or more. Okay, so in other words, I need to determine what is the probability of getting 4 or more. And we could go back to table 3 and just add up P4 plus P5 plus all the way on up to 15, although a lot of those are 0. So we could do that, but as long as I've already got the distribution pulled up here, I can just do 4, and then I want P of 4 or more. All right. So in other words, P of 4 or more is equal to 0.05556, which if you go to table 3 and add those up, it might differ a little in the last decimal place. Okay, so the point is, because this probability is greater than the threshold, the 5% threshold, okay, 0.05, we would conclude that no. Okay, that probability is greater than 5%, so this is not unusual. All right, so let me go on to problem number 2, which I did not have a chance to get to at all yesterday. So Clarinex D, purpose is to reduce the symptoms associated with allergies. In clinical trials, 5% of the patients experienced insomnia. All right, so experiencing the insomnia is what we would call the success in this case, and 5% is the probability of success. So in other words, P is equal to 0.05. That's how you would write 5% in decimal form. Part A, if 240 users, all right, so right there, we've got our sample size, 240, are randomly selected, how many would we expect to experience insomnia as a side effect? So this is basically just asking us to calculate the mean. It's saying in the long run, you know, out of 240 people, how many would have insomnia? So in other words, the mean, the number of people we would expect, which is equal to N times P, would be 240 times 0.05, and if you multiply that out, you should get 12. So the mean number of people would be 12. What is the probability that exactly 12 users out of the 240 will experience insomnia. So in other words, this is asking us to calculate P of exactly 12. Now, in this case, we cannot look it up in the table because the sample size is 240. The table does not go up to a sample size of 240. I think it has a maximum of n equals 20. So, of course, we can do it with technology. If you were doing it in the classroom, the only other option would be to use the formula and calculate it by hand. So remember that the formula for P of x for a particular value of x, which in this case is 12, is NCX times P raised to the x times 1 minus P raised to the n minus x. All right, and we have all these numbers. X is 12, n is 240, P is 0.05. All right, so you just have to substitute all those values in. Pause this for a moment if you want to go ahead and try to calculate that on your own before I show you the solution. All right. So what you're doing is you're doing 240 C12, and you should be able to do that on your calculator. Then you're doing 0.05 raised to the 12. And then you're doing 1 minus 0.05, which is 0.95, raised to the 240 minus 12, which would be 228. So if you do all that on your calculator, multiply it out, you should get 0.117. Okay. We can check that by bringing back this. So our sample size is 240, probability of success 0.05. I'm going to go ahead and hit enter. We're looking specifically at x equals 12, and I just want the probability that it is equal to 12. So I'm just going to hit enter, 0.117. All right, part C, what is the shape of the probability distribution and how do you know? So I'm going to erase all this stuff. Again, let's go back up to here where we're talking about the shape of the distribution. So the effect of the probability, and again, our probability is 0.05, which is much less than 0.5, which would put us over here. However, our sample size n of 240 is very large. So we have to consider both of these effects. In this case, if we calculate n times p times 1 minus p, so then we have 240 times 0.05 times 0.95, and if you multiply all that out, we get 11.4. And again, if you come down here to the bottom, if that number is greater than 10, then it will be approximately bell-shaped. So we would expect that this distribution is bell-shaped. And in fact, I already showed you the plot of the distribution right here. And you can see that it is pretty much bell-shaped. Okay. So now if I come down here to the last part of the problem, D, would it be unusual to observe 20 patients experiencing insomnia as a side effect? And how did you determine that? All right. Well, we already have the mean. We already calculated above that the mean is equal to 12. So now what I'm going to do is I'm going to calculate the standard deviation. Because this is a bell-shaped distribution, we already determined that, we can use the empirical rule here for determining whether or not there are unusual results. Okay, we can use the empirical rule if the distribution is approximately bell-shaped. All right, so that's what we're going to do here. I know the mean. I need to calculate my standard deviation, which is equal to the square root of n, which is 240, times p, which is 0.05, times 1 minus p, which is 0.95. All right, so go ahead and calculate that. And you should find that the standard deviation is about 3.4. So that's rounded to 1 decimal place. We know that our mean is 12, and we are trying to see if 20 is unusual. That's up here. So here's 18, 19, here's 20. So I don't care about the lower end of the curve. I only care what would be the maximum usual. And like I showed you when we went over the empirical rule, the max usual, using the empirical rule, would be mu plus 2 sigma. All right, so if I take my mean, which is 12, plus 2 times, we just calculated that sigma is 3.4. And if you calculate that, you would see that the maximum usual would be, hold on, I gotta calculate this real quick, about 18.8. So that would be like here. So again, we're just setting up these boundary values. Here is my max usual. Anything greater than that is unusual. So in other words, yes, it would be unusual to see that many people having insomnia.